Welcome everybody. Today's lecture will be on eigenvalues and eigenvectors. If you've had linear algebra before, you know this subject. If you haven't, don't worry. I'll teach you all you need to know for a class in ordinary differential equations. We'll begin to use these ideas in the next chapter. So let's get started now. And for some students, the word, just the names are confusing. Don't worry about where the names come from, okay? So suppose we have a matrix A, okay? And it's going to be a square matrix. Okay. If AX equals lambda X, we say lambda, which can be a complex, let's say for some, lambda can be a complex number. Even if you start with a matrix that has only real entries, very often your eigenvalue comes out to be complex. So we say lambda is an eigenvalue of A, which I abbreviate from now on as EV. So EV means eigenvalue for me. Okay, that's my personal thing, but you know I like to abbreviate so that, and I have to write a lot, so we'll use EV for eigenvalue. And the vector, the corresponding, and the vector X is the corresponding eigenvector. Now I can't use EV for eigenvector because I've already used it for eigenvalue, and we need to distinguish. So what's my favorite abbreviation for that? EVEC. Okay, then there's no confusion. An eigenvalue is EV, an eigenvector is EVEC. Okay. All right, don't worry about why these are important right now. We'll see it in a lecture or two. But just take it as a strange thing about matrices that you have to find that turns out to be important. They come up all over the place, okay? So let's see, I used asterisk before, so let me use star for this, okay? So notice, star holds if and only if AX minus lambda X equals 0. And now I can factor as long as I'm with matrices, as long as I'm careful. What do I mean by as long as I'm careful? I need to know my right hand from my left hand. Lambda's on the left. And I can't write, here's what I cannot write. I'll scribble it over here. I can't write A minus lambda times X equals 0. Okay, you can't write that. Why? Because lambda is a complex number, and this is a matrix. And a matrix minus a number doesn't have a meaning. So you can't write that. So how can you make sense out of it? You put lambda times the identity matrix. And that's what you really mean by that, okay? All right, so star holds, so this is just a warning, don't do this. If you write that, you will lose points because it doesn't make any sense, okay? So star holds if and only if A minus lambda I X equals 0. Let me just say note, 0 can never be an eigenvector. So this means a 0 vector, not the number 0, can never be an eigenvector. I should have included it in up here, the corresponding non-trivial. Eigenvectors cannot be the 0 vector, okay? So we need to know, when does this equation have non-trivial solutions? But a minus lambda I x equals 0 has non-trivial solutions if and only if the determinant of a minus lambda I equals 0. Okay? So the bottom line is to find an eigenvalue given A, solve the determinant of A minus lambda I equals 0 to find the eigenvalues. Okay. All right. Okay. So, and then we'll talk about how to find the eigenvectors. And I'll do that first in the context of an example, because it's hard to write it down in general, a general formula for doing it. But let me say something before we do this, before we do one. Notice if X is an eigenvector for A corresponding to the eigenvalue lambda, then C times X is also an eigenvector for lambda, for any C not equal to 0, C real. Okay, so any real multiple of it is also an eigenvector. So thus often we want eigenvectors with length 1, which we really should say the norm 1. And recall, if X is a vector, is a column vector. We're mostly doing this for column vectors. Then the norm of X is X inner product X square rooted, which is X transpose times X. So let's begin with an example. Okay, so I want to take this matrix and I want to find the eigenvalues and the eigenvectors, the corresponding eigenvectors for this matrix. Okay, so the first thing we need to do is to write down A minus lambda I. So that means lambda times the identity. So when you subtract, you get this. And notice you can do A minus lambda I just means basically on every matrix, subtract lambda off the main diagonal. So you don't really have to write it out once you figure that pattern out. And now to find the eigenvalues, we set the determinant of A minus lambda I equal to 0 and solve the equation we get in lambda. So for a 2 by 2 matrix, that's really easy. You just cross multiply. So I write down what I get when I cross multiply here. And now you do a little algebra. You have to multiply this out because you can't solve it that way. Your algebra skills have to be good or you're absolutely lost on these problems. So I get a -6 and then I get a minus lambda because I get a +2 lambda and a -3 lambda. So that's a minus lambda plus lambda squared plus 4. So that becomes lambda squared minus lambda minus 2. So that factors to lambda minus 2, lambda plus 1. So our two eigenvalues are 2 and -1. So if I call, let's call this lambda sub 2. So we remember it's the eigenvalue that goes with 2. Let's call it 2. Now we have to find the corresponding eigenvector, the x2. So what does that mean? We need to find a 2-component vector, because it's a 2 by 2 matrix, such that when I take the matrix A times x2, I get 2 times x2. A times the eigenvector gives you the eigenvalue times that eigenvector again. And then you solve for that x2 by putting everything on one side and looking at the equation A minus 2 times the identity times x equals 0. All right, so what do I mean by that? Here's the matrix A, subtracting 2 times the identity from it. So that means I take A and I subtract 2 off the main diagonal. I multiply by my vector x2, which I'm calling the components x and y. Those are the ones I have to find, and that equals 0. The 0 matrix, that is. Okay, so that gives me 2 equations. When you write down those 2 equations, you see that they are the same exact equation. Okay. In other words, what it tells you, those 2 equations both tell you the same thing, that x has to be equal to y. In other words, pick a value for x, and then y has to have the same value. So here's an eigenvector, E-vec. Here's an eigenvector is 1, 1. But so would 2, 2, so would 3, 3, so would minus 50, minus 50. All of them are eigenvectors, because any multiple of an eigenvector is also an eigenvector. All right, so let's call this x of minus 1. Okay, so that when you look at the eigenvalue minus 1, now you have to take A minus 1 times the identity. So that means A plus the identity times x times the eigenvector that we're looking for is equal to 0. Let's call the components of the one we're looking for z and w. Name them anything, okay? And now you look at A plus the identity, okay, because that's A minus 1 times the identity. This is what you get for that matrix, times the eigenvector, the unknown vector, has to equal the 0 vector. Okay. So now when you write down what those equations say, they're both the same exact equation. 4z minus w equals 0. So w is 4 times z. So if you pick z to be 1, then w has to be 4. So here's an eigenvector for minus 1. And any multiple of this is also an eigenvector for minus 1. Okay, so that's your answer. You found your 2 eigenvalues and your 2 corresponding eigenvectors. All right, let's look at one where it's not quite as trivial, because 3 by 3s are always harder, even though this is a pretty easy one, because the algebra can get really messy on this. All right, we asked to find the eigenvalues and eigenvectors for this matrix. Okay, so we first start looking at where the determinant of A minus lambda I equals 0. So here's A minus lambda I. Now I have to take the determinant of that. Determinants of 3 by 3s are no picnic, but we'll write it out. So I'm going to go right along the first the first row. So minus lambda times what I get when I delete the row in the column containing that. Excuse me. Then minus 1, delete the row in the column containing minus 1. And then plus 1, and delete the row in the column containing plus 1. Now it's 2 by 2, so you can just cross multiply to get the determinants of those. And when you write that all out, you get this. And now algebra schools will really get you in trouble, because these are in general not easy to solve. And to track through the algebra without making a mistake is non-trivial. Okay, so I'm going to handle this in a kind of slick way. This one factors to lambda plus 1 and lambda minus 1. If I distribute the minus sign inside, I see I get plus lambda plus 1. And this one's also lambda plus 1. So there's 3 separate terms, all of which have a common factor of lambda plus 1. Great, let's factor that lambda plus 1 out. Now what do I get when I do that? So here I'll get a minus lambda squared, then a plus lambda. From this term, factoring out the lambda plus 1, I get a 1. Same thing from that one. So that means I have lambda plus 1 is minus lambda squared plus lambda plus 2. Let me go ahead. I like to factor things when the coefficient in front of the highest order term is positive. So I'm going to factor out a minus 1 and divide by it. So I'll get a 0 is this. then this becomes lambda squared minus lambda minus 2, which also factors to lambda minus 2, lambda plus 1. So notice this is lambda plus 1 quantity squared times lambda minus 2. Okay, that means lambda equal minus 1 is an eigenvalue of multiplicity 2 because the term involved that it comes from has a power of 2 here. And lambda equals 2 is an eigenvalue of multiplicity 1. So this one has multiplicity 2. Okay. All right, and now we want to find the corresponding eigenvectors. All right, so let's go with lambda equals 2 first. Let me call it lambda 2. Okay. So we need to look at a minus 2 times the identity times the eigenvector that goes with that guy equals 0. That's the equation that you'll use to find the eigenvector. And here an eigenvector has to have 3 components. So let me call them x, y, z. Okay. So when I subtract 2 times the identity from this matrix A, I get minus 2, 1, 1. And let me just make sure it was plus 2. Yes, it was. Okay. And then that's 1 minus 2, 1, 1, 1 minus 2 times x, y, z is equal to 0, 0, 0. Okay, so that means I have 3 equations and 3 unknowns. Multiplying the matrices together. This is matrix multiplication to give me this. Okay, so that's 3 equations and 3 unknowns. We have to solve for x, y, and z. So I write them in a big matrix. And now I use row reduction to solve for these things. So I'm going to do minus 1/2 times row 1. So that'll give me 1 minus 1/2 minus 1/2, 0. And to get rid of the 1 here, I'll do minus 1 times row 1 and add it to row 2. That'll give me minus 1 and plus 1 is 0, plus 1/2 and minus 2. Minus 2 is minus 4 halves, plus 1/2 is minus 3 halves. And then I get plus 1/2 and 1 is 3 halves. Okay, let me make sure I did that right, because if you botch up the arithmetic, you'll be in trouble. So this is plus 1/2, and that's minus 4. Yes, okay, that's right. And then this is plus 1/2, and 1 is 3 halves. Okay, and then I get 0. And now to get rid of this one, I'll do minus 1 times row 1 and add it to row 3. So I'll get 0. I get plus 1/2, and 1 is 3 halves. And then I get plus 1/2, and minus 4 halves is minus 3 halves. 0. Okay. So notice if I just go ahead right now and add row 2 and row 3 and put that in row 3, I get a row of all zeros. And just like in the 2x2s, one equation has to turn out to be exactly the same as the other. If you don't get a row of all zeros when you're doing a 3x3 calculation, you made a mistake. One of those equations has to be extraneous. Okay, things have to go away. Okay, so this is a check to yourself when you're doing it. If you don't get this by this point, you did something wrong. So here we'll do minus 2/3 times row 2. So I'll get 0, 1, minus 1, 0. And now I'll do 1/2 times row 2 and add it to row 1. So I'll get 0 and 1 is 1. Oh, sorry. 0 and 1 is 1. 0, 1/2 and minus 1/2 is 0. And then I get minus 1/2 and minus 1/2 is minus 1. And then I get 0. And that's the best I can do with clearing. So this first equation says that x minus z equals 0. So that x is equal to z. And the second one says that y minus z equals 0. So that says y is equal to z. So you pick z to be anything you want. I'm going to pick z equals 1. And x and y are both 1 by what we just found here. So that means my eigenvector is 1, 1, 1. Okay. And any multiple of that is also an eigenvector. Okay, that's just one of them. Now we have to find the eigenvector for lambda equals -1, because that was our other eigenvector, eigenvalue rather. Okay, so now we start the same game again with lambda equals -1. So we have to look at A minus a -1 times the identity times its eigenvector has to be the 0 vector. So let me call x minus 1 ZWU. Okay, it has 3 unknowns. Okay, so when you take A and you add the identity to it, let's look at A again. Where did my A go? It's my page with A. It's my A. So I add the identity to this matrix. That's going to give me 1, 1, 1, 1, 1, 1, 1, 1, 1 times ZWU equals 0, 0, 0. Okay, so that gives me 3 equations and 3 unknowns. I'll let you write that out. And then you have to solve them simultaneously, which means you have to work with this system. Okay, now it's kind of not hard to see what's going to happen here. You write down the first row. And now you say minus row 1 and add it to row 2, and minus row 1 and add it to row 3. And when you do that, you will get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And that's okay. That's not bad, because this first row tells you the information. It says x plus y plus z equals, I'm sorry, we called it z. It should be z plus w plus u equals 0. Let me not squeeze this in so bad. Here. So it says z plus w plus u equals 0. So remember that -1 was an eigenvalue of multiplicity 2. So we would like 2 linearly independent eigenvectors. Okay, that's what you would like to have. Can't always do that, but when you have real coefficients in your matrix, you can. That's not quite true, but anyway, in this case, you can. Okay, so what that means is since this is our only constraint, we can pick 2 of z, w, and u, and the third is given by the equation. So let's pick, and you want to pick it so that it's linearly independent. So I'm going to pick z equals 1, w equals 0, and then u will be 1 plus 0 plus u equals 0, so u will be -1. And then I'm going to pick z equals 0 and w equals 1. And then by this equation, that will say that u is equal to -1. So here are my 2 eigenvectors corresponding to -1. I don't know, let me call it lambda -1. So that was z is 1, w is 0, u is -1. And the second one, I don't know, let's call it hat. Give it any name you like. That'll be 0, 1, -1. And by choosing the 1, 0, 0, 1, like 1, 0, 0, 1, you are sure that these come out to be linearly independent eigenvectors. You know, if you pick them and mess around too much, you might end up picking linearly dependent eigenvectors, and then at the next stage of the game, when we use this, you'd have to redo it and find 2 different ones. Okay. So now we have our 3 eigenvectors and all the eigenvalues for that matrix A. Okay, so you just have to practice on those, and it takes a lot of practice, and it's a fair amount of calculations. So it's really is sort of non-trivial to do these problems. The last thing I want to point out, the last thing I want to point out is a theorem about for self-adjoint matrices. Okay, so before that, I even give the theorem, let me give you a definition. So hold on for a minute. So here's the definition. A matrix A, a square matrix A, is self-adjoint or another word for that is Hermitian. Hermitian, if, I'm sorry, ITIAN. If A is self-adjoint, also known as Hermitian, if A star is equal to A. And remember, A star is a conjugate transpose, which is the same thing as A transpose conjugate, okay? So let me say it on a separate sheet on the next sheet of paper, because this is a bit long of a theorem. If A is self-adjoint, then 1, all the eigenvalues of A are real. All the corresponding, let me say it this way, all the eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, remember what that means here. Orthogonal means that X, inner product X is equal to 0. The bracket. Let me say, add is if X1 and X2 are eigenvectors corresponding to distinct eigenvalues, then X1, open bracket, X2 equals 0. Okay, so they're orthogonal to each other. 3, there is, oh, geez, always with the pens, they don't last the whole lecture. Yeah, this one's empty. Hold on a second. So there always exist n linearly independent eigenvectors. So if A is, let me make it n by n and self-adjoint, then there exist n linearly independent eigenvectors for A. Okay, so we call that a full set because you have at most n eigenvalues. They don't all have to be distinct. But what that means is that even if you have an eigenvalue that has multiplicity k, then you must have k linearly independent eigenvectors corresponding to that eigenvalue. That's not always true for a general matrix. The example we just did, we had an eigenvalue of multiplicity 2, and we found 2 linearly independent eigenvectors for that eigenvalue. That doesn't always have to be true for a general matrix. Okay. All right, and then finally, we can always choose um, a full set, that means n, of eigenvectors so that any two eigenvectors um, are mutually orthogonal. Well, so that any two are orthogonal mutually is redundant there. Okay. Now that actually is a trivial consequence of once you can get a full set. That doesn't really, that's a trivial consequence of that. But the point is that if, um, whoops, sorry. So thus, for a self-adjoint matrix, if an eigenvalue has multiplicity k, then there exists k linearly independent eigenvectors corresponding to that eigenvalue. Okay. Okay. So I know that's for those of you who have not had linear algebra, it seems like an awful lot of information. For those of you who've had linear algebra, there's nothing new in here for you. Okay. But anyway, that's the very condensed version of only what you need to know to be able to work the problems and use it in the next sections. Because what we'll start in the next section is looking at systems of ordinary differential equations, writing it out in matrix format, and then using some of these properties to solve the systems. And that's basically it for the semester. Okay. Okay, so that's really all we need to know about eigenvalues and eigenvectors in order to be able to carry out our calculations in the next chapter for systems of linear ODEs. Okay, so see you soon. Bye.